Assalamualaikum and good day everyone. So we will cover the last part of the week 13 lecture, okay, which is the design of a synchronous counter. Okay, so here we will start to learn about how to design our counters. Okay, so without further ado, we start. A synchronous counter consists of two major parts, namely flip-flop and next state logic, right? I think this one is everyone already know it. Okay, as illustrated in this figure 13.29. Flip-flop holds the present state or current value of the counter. The next state logic prepare the next state or the new counter value when a clock pulse is received. So when upon trigger by the clock pulse, then the next state logic will prepare the next state, okay, or the new counter value. Okay, the counting sequence is therefore determined by the design of the next state logic. So you see here is the counter architecture, and here is your flip-flop, and this is your counter output. Then you see there's a feedback towards the next state logic. Okay, so this is your present state. Then from the flip-flop will hold the present state or the current value until it is triggered by a clock pulse. Okay, table 13.3 summarize the step, okay, in designing our own counters. Okay, so this step you need to follow, okay, because it is start from the more simple step until actually you manage to construct your counters. Okay, so an important part of the design process is determining the required input to a flip-flop to make it go from particular present state to a desired state. So let's say if you want to design a counter that count from 0 until 2, so we need to make sure that it will able to count from 0, 1, 2 and then return back to 0. Okay, that is one of the first part, okay, of our design. So an important part of design process is determining the required input to a flip-flop to make it go from particular present state to a desired next step. In this step, we must refer to the flip-flop excitation table. Okay, this is example of the flip-flop excitation table, table 13.4. The derivation of the excitation table may be reviewed in section 11.45. Okay, you guys can see this in the previous lecture where you guys have learned it. Okay, so if you guys see first, okay, for first step, okay, we need to graphically show the counting sequence. Okay, we must able to imagine how it would be, and we will make into a counter state diagram. Okay, we make a state diagram, and then state table, we convert this state diagram into our state table. Okay, where we're going to actually specify the value for the present state and also the next state. Then the flip-flop inputs, okay, by referring to the excitation table, we will add another set of column listing the necessary flip-flop inputs, okay, that will produce that present state and next state. Okay, input expression, we extract the boolean expression for flip-flop inputs. Then the last step, we implement that. We construct the counters. Okay, so we need to follow this step one by one. Okay, if you see from the excitation table, you can see there's a state Q. This is present state. This one is the next state, and our input can be from the D flip-flop, T flip-flop, JK flip-flop, and SR latch. Okay, so without further ado, we go to for the example. Okay, counter design with T flip-flop. Sequential counters are commonly designed using T or JK flip-flop to reduce the amount of next state logic. For our first example, we are going to design a mod 8 binary counter. Okay, mod 8 binary counter. So it's a binary counter using T flip-flop. If you see, there is a mod 8 binary counter. So mean it is from 0 until 1, until 7. Okay, because 0, 1, 2, 3, 4, 5, 6, 7. So 7 decimal. But if we need to change into our corresponding binary, okay, which is this. Okay. So the first step, okay, the first step, you have the state diagram. Okay, you need to draw your state diagram. Use the state diagram for mod 8 binary counter is shown in figure 13.30. Okay, if you can see, we start from 0, 0, 0 in order, then we start, then follow by 0, 0, 1, 0, 1, 0 until we have to the 8th state, then we return back to our 0, 0, 0. Okay, so then after we manage to produce our state diagram, we will produce our the state table. Okay, the state table shows the same information as the state diagram, but the information is in table form. Okay, as you can see, for example, when the present state is 0, 0, 0, the next state is 0, 0, 1. Okay, you can see the order. Okay, when 0, 0, 1, the next state will be 0, 1, 0. So this is your state table. After you finish with your state table, you can relate your table with the relevant flip-flop input. Okay, the required flip-flop input are found by referring to the excitation table for T flip-flop. Okay, for example, examine the first row where the present state is 0, 0, 0 and the next state is 0, 0, 1. Okay, if you can see, there is no changes for Q2 and Q1 for the present state to the next step, but we can see there is changes for Q0 from the present state to the Q0 plus. So means at this stage you need to do some things. Okay, so the first two flip-flop must maintain the value of 0, therefore the input are both 0 because it's more maintained. However, the least significant flip-flop must toggle. Okay, because we see it is 0 toggle to 1, so this is toggle 1. Okay, continue setting the value for all flip-flop until all has state have been accounted. Okay, you will continue this until this 1, 1, 1, and then until you solve for the next state as well. Okay, so you see this is 1, 1, 1, so the next state will 0, 0, 0 here for the next state. So what is the corresponding TF input? Okay, for the T flip-flop is 1, 1, and 1. After that, once you finish with your state table and state table which have this present state, next state, and T flip-flop, you're going to make an input expression. Okay, you can use K-map. Okay, for the state table, derive the Boolean expression for all flip-flop inputs. You have 3 here. The Carnot map and the derived Boolean expression are shown in figure 13.31. So, okay, so first you need to make a K-map, and then you loop your 1. Okay, for here T2 equals Q1 Q0, T1 is Q0, and T0 is 1. Okay, so next you will implement to our count. Okay, we implement where we're going to construct our counter. Okay, finally we draw the schematic as shown in figure 13.32. Okay, if you see, this is your T0. Okay, if you T0, you can see it is 1, so that's why the first flip-flop you have 1 value. And how about T1? T1 is equals to Q0. That's why the input of the T1 here is Q0. Okay, the next is T flip-flop of the third T flip-flop, Q1, Q0. Okay, Q1 end with Q0. So you have Q1 end with Q0, then you have this T2. Okay, I think this is quite straightforward, okay, and easy to understand. Next, we go to this counter design with JK flip-flop. For our second counter design example, we will design a gray code counter with JK flip-flop. So this we go back to your earlier chapter, okay, where you need to know about binary, how to convert binary to gray code, how to convert gray code to ASCII, something like that, okay, XS3. So if you didn't know about this, then it will be a problem because you will not able to answer correctly the rest of the question, okay. So make sure you are well versed in this binary, XS3, gray code, and so forth, okay, the required relevant knowledge, because this chapter design require you to have a strong knowledge of the earlier chapter, okay. So the next example is that we want to design a gray code counter with JK flip-flop, okay. So first, of course, we need to have our state diagram, okay. You can see is zero 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 going to 0 0 1, and then 0 1 1, and then 0 1 0, 1 1 0, 1 1 1, 1 0 1, 1 0 0, and go back to 0 0 0. So this is example of 3-bit gray code counter state diagram. So how we actually have this order, you guys, if you forget, please refer to the previous lecture, and of course from the book itself, okay. Next, when we have the state diagram, we derive our state table, okay, which we have our present state, and then we have next state, okay. So if you see, this is your present state, this is your next state, you just transfer from your state diagram to your state table, and after that what happened is that you're going to relate this present state, next state with your relevant flip-flop inputs, okay. So 3 JK flip-flop has 6 inputs, correct? That means 6 new columns are added to the state table at the excitation input for all flip-flop to get table 13.8, okay. Remember, you need to be very observant, very careful, read your question very well. It mentions specifically to design gray code with JK flip-flop, okay. So you guys know JK flip-flop have 2 input, right? So in order to have 3 JK flip-flop, you will have 6 input then, okay. So the same goes as what we learned in the previous examples, okay. You draw out your JK flip-flop inputs, okay. This one, if you guys didn't forget, please refer to your module, the operation of JK flip-flop, okay. It is just like a set, reset, and so forth, okay. After we manage to come out with our flip-flop input irrelevant with present state and next state, we're going to derive our expression, okay. Using kernel map or other method, we will then get our Boolean expression for all flip-flop inputs. We will get this, okay. Then after that, we're going to implement, okay, where we're going to construct our counters. So this one, I hope you guys can try it, okay. Try it, and you guys hopefully that you get a counter that actually satisfy this expression, okay. So we finish with our design counters. So I hope that each of you in the group, in your own group, try exercise 13.1, 13.2, 13.3, 13.4, 13.5, 13.6, 13.7, 13.8, 13.9, 13.10, okay. And if you guys didn't have book, don't worry, you guys can refer to the e-learning where Hui already upload this photo. Okay, so I hope that you guys will use the time, okay, the time to actually do this exercise, okay, in your group to discuss, and of course to share the answer in the e-learning. So let me know if you guys have any problem so far. So far the previous problems that, I mean the previous request is on the exercise of module 9, right? Okay, so I hope you guys all try this, okay, try this, and before the next week's lecture, okay, try before the next week lecture 13.1 until 13.10. Okay, so with that we finish our lecture. So see you guys and have a nice day.